Hello, and welcome to the tutorial on bond market conventions. Bond market conventions relate to how we interpret market quotes for bond yield and price. Yield to maturity quotes relate to coupon payment frequency, and coupons are typically paid semi-annually in the US, but more typically annually outside the US. And so yield to maturity quotes by convention assume the compounding frequency equal to the coupon payment frequency. And price quotes relate to the adjustment for accrued interest. So quoted prices in the market for bonds exclude accrued interest, which means that when we settle the bond, when we settle a trade, we actually have to add that accrued interest back in to get the cash price paid. How we calculate that accrued interest varies slightly according to the bond type and market convention. So let's start with yield to maturity and coupon payment frequency. So clearly, if we have a more frequent coupon payment, we're getting interest more frequently, and we're getting interest on interest. And so the effective annual rate that we get, which reflects the compounding, will be higher. So if we have a semi-annual bond, we will take the quoted rate divided by 2 and square that to compound it, and that will be the effective annual rate. Now let's look at an example. Suppose we have a bond that is quoted 6% per annum, but it's paid monthly. So in this case, we have 6% divided by 12, or 1/2% per month paid. But since we're getting it every month, we can reinvest it, and that's compounded. So that 1/2% compounded every month for 12 months works out to be an effective annual rate of 6.17%, which is a bit over the quoted rate of 6%, reflecting the benefit of the compounding. And of course, if we have a higher rate, say 18%, compounding also over 12 months, we're getting 1.5%, compounding that over 12 months, we're going to get 19.56%. Because it's a higher rate, so we're getting more interest more frequently, the difference is larger. And so we see that here, 19.56 versus 18% quoted. Now let's look at how this works out for two important bonds that are traded, US Treasury bonds and Euro bonds. US Treasury bonds are semi-annual pay. And so by convention in the US, a yield to maturity is quoted on a semi-annual bond basis, and that will apply for most corporates as well. Outside the US and in the Euro market, it's more common for the coupon to be paid annually. And so again, following the convention, the yield to maturity will be on an annual bond basis. So if we look at how this works out in terms of numbers, if we see a 10-year maturity with a 5% coupon and a price of 100, for the US Treasury bond, that means we're actually getting 2.5% coupon every 6 months. And since the yield to maturity convention is to match the coupons, the yield to maturity will show up as 5%, because effectively 5% on a semi-annual bond basis means 2.5% every 6 months. But then when we compound that to put it on an annual basis, we get an effective annual rate reflecting that compounding, and that will be a bit higher, 5.06% in this case. Now, if we're looking at Euro bonds, there's no adjustment. Assuming the same 10-year maturity, same 5% coupon, same price of 100, but critically the 5% coupon is every 12 months. And so the yield to maturity is going to be the same as the effective annual rate. So if we're comparing these two bonds, the US Treasury would have an effective annual rate of 5.06, and the Euro bond, because it's getting its coupon less frequently and is being quoted less frequently, the yield to maturity would be reflecting that, will have a lower yield. Okay, so let's look at how we would do this on our calculator. Suppose we have a 10-year bullet bond with a coupon of 10.5%, and it's paid semi-annually, and the price is 125, and we want to know the yield to maturity. And since it's a semi-annual bond, we want the yield to maturity on a semi-annual bond basis. So how do we do this? Well, we need to convert everything to periods, because essentially semi-annual bond basis means it's the 6-month rate times 2. So we have to say, well, what are we going to get every 6 months? And so we convert number of periods, 10 years times 2 gives us 20 periods. Payment per period is going to be 10.5. The coupon divided by 2, 5.25. The price is 125, and then that's going to be our yield for 6 months, 3.4922. But then to make it a per annum semi-annual bond basis yield, we have to multiply that by 2, and we get 6.9844. So when we say the yield to maturity is 6.9844 on a semi-annual bond basis, what we mean is it's half that every 6 months. So what if we go the other direction and we have the yield to maturity on a semi-annual bond basis, 6.9844, and we want to calculate the price? Well, everything's going to stay the same in terms of inputs. We're going to still have 20 periods. We're still going to have payment of 5.25 every 6 months. And in this case, we're inputting the yield of 1/2 of 69844, or the 34922. And we're getting our present value back, which is almost 125. The difference here is just due to a rounding on the input yield. Now, when we're making comparisons between bonds with different compounding conventions, we need to convert them to become a common one. So this typically arises when we're comparing the yield on a US dollar denominated Eurobond, and we want to look at its spread relative to US Treasury bonds. And the Eurobond's on an annual bond basis by convention, the yield, and the Treasury is on a semi-annual bond basis. So what we need to do is convert the annual bond basis yield to a semi-annual bond basis yield, and that's done essentially by decompounding that rate. So we're getting some rate for 12 months, and 1 plus that rate, we decompound it for half a year. That's what the 0.5 is, subtract 1 to convert that to a rate. So then this will be the rate that we would get over every 6 months. And then we multiply that by 2, and that will give us the yield on a semi-annual bond basis. And then to convert, to look at that as a spread over treasuries, we would take that yield and we would subtract the treasury yield, which is already on a semi-annual bond basis. So let's just look at an illustration to make sure this is clear. So let's say the Eurobond has a yield to maturity of 7.5% annual bond basis, and the US Treasury has a yield of 2.5% semi-annual bond basis, and we want to know the spread over treasuries. So we're going to do the conversion using the deconversion formula. So we're going to take that 1 plus the 7.5% for half a year and say how much would we get every 6 months such that it would compound to 7.5%, and that's what we get here. And then we multiply that result by 2 and we get 7.36%. So essentially what that means is it means 7.36% divided by 2 compounded is going to give you the 7.5%. So that's why this is a semi-annual bond basis equivalent. And then we subtract from that the 2.5%, since they're both now SABB, and the difference is 486 basis points. Now, yield to maturity quoting conventions will also affect how interest rate sensitivity is measured. Not by a lot, but by enough to make a difference in some cases. The PVBP, remember, PVBP stands for price value of a basis point. And the basis point that we're measuring is a basis point in yield. So it matters whether that's on an annual bond basis or a semi-annual bond basis. So typically, if we're quoting our yield on a semi-annual bond basis, we would measure the shift in that yield, which means really 1/2 basis point per year is what a 1 basis point per annum shift is. And so if we're hedging bonds then that have different yield to maturities, different conventions, annual bond basis or semi-annual bond basis, we need to make sure they're converted to be the same basis so that we have an accurate hedge. The same effect is going to slightly affect unmeasured numbers for modified duration and DV01. So if you're setting up a model with a portfolio that has bonds that are some are semi-annual bond basis and annual bond basis, to get an accurate portfolio measure, you need to be clear. Okay, what are you measuring? Are you measuring the modified duration and DV01 for that portfolio on an annual basis or a semi-annual basis? Now let's just look at how the PVBP would be done for semi-annual bonds. So in this case, we're going to have a 4% bond. It's a 10-year bullet, and it's a price of 78. So we're going to convert our 10 years to 20 periods here. Our 4% coupon is two per payment period, 2 every 6 months, price of 78. And then this is our yield for 6 months for the one semi-annual period. And then we need to essentially subtract a half a basis point from that to find the PVBP. Now, if we're going to do this precisely, you may remember from the previous tutorial on interest rate sensitivity that we can divide that by 100 and then multiply the result by 100, and that'll give us a more precise measure of the linear PVBP. And so we'll do that in this example. So we reclaim the yield from up here, the 3.5558. We subtract half a basis point divided by 100, and that'll be actually this number here if we're looking to more decimal places. We compute the PV, and again, if we're looking to more decimal places, we'll see it out here. We subtract 78, we multiply that by 100, and we get our PVBP of 0.0608 in this case. And notice this 100 here is just reversing the effect of this. So the other way we could do it is not divide by 100, not multiply by 100, and we'd get a very similar number here, but we'd have a slight error, and it would carry over into our next calculation on modified duration. So modified duration for a semi-annual bond is actually done once you've done the PVBP calculation, as done on the previous slide. It's the same as we would do it with an annual pay bond, because the effect of the semi-annual basis is already reflected in the PVBP. So we've measured that, and we then just take that number, we divide it by 78, and then we divide that by 0.01% or multiply by 10,000, and that gives us the 7.7918. Again, if we were doing the less accurate version of this, we're trying to be quicker and didn't divide by 100 and multiply by 100 there, we would get something slightly different in these decimal places here. So it wouldn't be a bad approximation. Now let's move on to the other aspect of bond market conventions, and that deals with the issue of accrued interest and how bond prices are quoted. Now, bonds are quoted on what's called a clean basis, which means a clean price basis, which means it does not include the accrued interest, or specifically it excludes or is net of accrued interest. There's something else called dirty price or full price, and that's what you actually are going to pay when you settle a trade, because you have to pay the clean price plus accrued interest. So the dirty price is that number. And these, in general, these will be different unless you're exactly at a point in time where the coupon was just paid. So the bond settles on a coupon payment date, so there is 0 accrued interest. So in that case, dirty and clean price will be the same. Now, another issue we should just highlight here is settlement, and everything is being measured from settlement. And generally, trade and settlement will be on different dates. Typically, it's 1 to 3 days after. So you'll do a trade on a Monday, and you may settle the trade on Tuesday, Wednesday, or Thursday. The settlement lag is measured in business days. So if you do the trade on a Friday, you're going to settle the trade then on Monday, Tuesday, or Wednesday. And just one other point is there's going to be a little bit of counterparty risk between the trade and settlement date. What that refers to is if one of the parties that agreed to the trade isn't able to settle and the prices have moved between the trade date and the settlement date, the party that doesn't get bonds or doesn't get cash could have a small loss. Okay, so in terms of accrued interest conventions, there are several, but there are two that are most common. One is actual, and that's what's used in U.S. Treasuries. And essentially, it just means that you count the actual number of days that have passed since the last payment, and you divide that by the total number of days in a coupon period. So if you're looking at semi-annual periods, they vary generally between 181 and 184 days. So not every semi-annual period will be the same. Now, 3360 convention tries to simplify that by assuming every month has 30 days and every year has 360 days. And particularly if you're looking at a semi-annual period, every semi-annual period would be 180 days. The difference between these two is not huge in terms of the actual accrued interest and its effect on yield to maturity. But if you're settling bond trades, you need to be exactly accurate. And if you're setting up models or systems, you of course want to reflect the proper conventions. So let's just see how this works. So essentially what's going on here is we have the last coupon payment date and the next coupon payment date, and we have a settlement in the middle. So we have the days in the coupon period, and then we have the days accrued. So when you settle the trade, you're going to need to pay extra for these days of accrued interest, or essentially for the fraction of the period represented by these days accrued relative to the period. So that's what we do. We have accrued interest equal to the days accrued divided by the days in the period, and we multiply that by the annual coupon rate divided by the frequency or the rate for the period. So let's look at an illustration of how this would work. And let's say we're dealing with a 5% coupon rate semi-annual bond basis. We got a trade date of May 11th. We settle, that's a Thursday, and say it settles on 3 business days later. So that'll be a Tuesday. So that's May 16th. And the period that we're in goes from February 15th to August 15th. Okay. So if we're doing this as, say this were a treasury bond, on an actual basis, we would measure the actual number of days between February 15th and May 16th. So that would actually be measured as 90 days. And remember, February is a short month, so that's why it's not more than 90. The actual days in this period is 181. So in the semi-annual period, it's 181. So the fraction of the period is given by this. So we're a little bit less than half a period. And then, of course, the coupon has to be divided by 2 because it's a semi-annual coupon. And so this would be the accrued interest that would be added to the quoted price when the trade settled. Now, if the same trade were being done on a 3360-day basis, well, every month is 30 days. So that means that there's 180 days in a 6-month period. And in this case, every month has 30 days, including February, which has 28 in reality, but it's counted as of 30. So the days difference here is 91, which is 1 day more than the actual number of days that have passed. And so we're going to get a slightly larger fraction because both numbers have changed. And you'll see the accrued interest in this case, assuming the same interest rate and assuming it's semi-annual. The accrued interest here would be 1.264. And so this would be the convention for US corporate. Okay, so not a huge difference, but if you're talking about millions of dollars, you will definitely care about those decimal place differences. All right, now when we're looking at mid-period settlement, it's important to just understand a little bit what's going on. So we have a trade that's settling in the middle of the period. So it means the cash flows aren't coming 1 period later, they're coming half a period later. And here we're dealing with periods. So this could be half a 6-month or half a year. So we've got the coupon coming in half a period, and then we've got another coupon. There'll be 1 period between each of these, but the time period between the settlement and this is 1/2. And then the actual settlement amount, the price we're going to pay is going to be the quoted price plus the accrued interest. So we're essentially paying for half of this accrued interest because we're going to get a full coupon even though we're only holding it for half a period. That's the concept. And so when we calculate yield to maturity on this, we want the yield to maturity that will basically balance this equation. And this is what your calculator would do, or more likely in this case, you'd be doing this in Excel, where you're showing the interest that's coming, and then you're compounding the yield to maturity for half a period, 1.5 periods, and 2.5 periods. And then that needs to equate to the full price that you're paying. And so the yield to maturity will be the yield that will make this equation equal. So let's do an illustration of evaluation with mid-period settlement. Suppose we have a U.S. Treasury note. It is a 5% coupon due in 9 months, and assume the current period is half over. So 91 days out of 182 have passed, and U.S. Treasuries are semi-annual, so there will be a coupon payment of 2.5 in 3 months and then 9 months, along with the principal of 100 in 9 months. And let's say the current yield to maturity is 8%, and this is a U.S. Treasury, so it's semi-annual bond basis. And we want to know, what are the dirty and clean price of the bond? Well, in terms of time, well, we've got half a period is a quarter of a year and 3/4 of a year, so that's reflecting 3 months and 9 months. These are our cash flows. So we're going to get the full coupon, even though we're only holding it for half a period. So we're going to get 2.5, and then we're going to get 102.5. And the yield to maturity, remember we said, is 8%. So 8% divided by 2 cents, 4% per period. And then the number of years that's going to be, it's going to be 1/4 of a year times 2 to convert that to periods. And so that will get the value of this cash flow. This 2.5 will be 2.451. So this is just discounting the 2.5 using semi-annual compounding and a fractional period. And we'll do the same thing then for the second cash flow. And the only thing that's different is the cash flows more, and the time is 3/4 of a year instead of 1/4. And so we'll get the present value at the yield to maturity for the second cash flow, and we add those together. So now what is that? Is that the price? Well, that's the dirty price, because that is the value. That's the total value that we would pay for this bond, and that includes the accrued interest. So we need to subtract the accrued interest to get the clean price. So the accrued interest in this case would be easy. It's just 1/2 period times 2.5, so 1 1/4. So we take the dirty price, we subtract the accrued interest, and we get the clean price. So that's it on bond market conventions. A lot of material. Let's just wrap up with some conclusions on this tutorial. So yield to maturity is calculated based on a bond's dirty price, since the PV of all future cash flows must equate to the full price paid. Yield to maturity is also by convention usually based on compounding frequency equal to the coupon payment frequency. The bonds paying coupons semi-annually, U.S. Treasury bonds, for example, express yield to maturity on a semi-annual bond basis. U.S. corporates also will do that. Bonds paying coupons annually, for example, Euro bonds, will express the yield on an annual bond basis. Important to remember that the interest rate sensitivity measures will be aligned, as a general rule, with the same basis convention as the yield to maturity, unless they're converted. And you might need to convert them if you're dealing with portfolios. Bond prices are quoted clean, without accrued interest. And when a bond trade settles, the cash paid will reflect the addition of the accrued interest, and that will be the full or dirty price. And then finally, accrued interest day count conventions will vary slightly, and that will give us slightly different differences in accrued interest. So that's it for this tutorial on bond market conventions. Thank you for listening.